Okay. So all I was saying, midterm solutions are out. If you're having trouble seeing your scores, let me know. We should be able to see your individual scores as well as the solution set under the midterm module. Lab 7 is due this upcoming Sunday. It was released last week, so we don't have Lab 8 until next week. Lab 8 is really meant to be practice for this, this data collection input modeling report that you're going to be generating as your first deliverable for your final project. So in Lab 8, I give you a bunch of data that looks a lot like data you'd collect at a system like a restaurant or a call center or something like that. And then you have to fit models to it. And so we're going to be learning how to do that in this unit as well as in the lab. And so that fitting process is going to be very similar to what you're going to do when you actually gather data for your own project and fit models to it. So after Lab 8, we will have sort of a gap in the lab schedule that's meant to provide you extra time to work with your newly formed project team to gather a little bit of input modeling data for your project and start fitting those models using the same sort of tools that you practiced within Lab 8. And then after that, we'll have Lab 9 and 10 on our normal weekly schedule. Those are more advanced topics in ARENA. And then the rest of the lab periods are kind of meant to provide you final project modeling help. So they're just sort of open labs where you can meet with a TA or make appointments with me or just generally work with your team. So the final project, the description is available in the final project module. You can find a sort of a readout of the general description, some information about what the report looks like, what the presentation looks like. The basic idea here is in groups of nominally 4 students, but you can probably take 3, but I'd like to have as many 4-person groups as possible. Then analyze a real world system of your choice, then using ARENA as your simulation model. As I mentioned before, if you'd like to use FlexSim or some of these other ARENA competitors, that's also possible. For ideas, if you go to say chapter 9 and look at exercises 1 through 5 in banks, they list a number of possibilities that I think are good to maybe get thinking, like a grocery store, a cafeteria, a traffic intersection, a laundromat. Also, as you're walking through ASU's campus, I think you'll see a bunch of good cases where some operations research could be done, like walk-only zones, how do you increase compliance, things like that. Many coffee shops, food services, classrooms, offices, the DART system, things like that. So there's a bunch of different opportunities where it would be very easy to observe these processes going on, take data on them, build a simple simulation model of them, and then try an intervention. So what if we had more of these resources? What if we used a different way to assemble this product, and so on and so forth? People have also done things like maybe their family owns a guitar making company and they happen to have data that they can gather from that. That's totally fine as well. There might be other systems where the data is already archived somewhere in a database that you've got, maybe working with an internship, maybe in a capstone project, maybe just available online. There's also things like there are these like webcams that watch intersections sort of all over the world. And if you'd like to observe those instead of a real, or instead of like an intersection, maybe you want a more high throughput intersection than some of the ones that are on ASU's campus, something like that, that's totally fine too. So there's a bunch of different options for how you pick the system here. Each group should hopefully again have 4 members, but 3 might be okay, but try to shoot for 4. And if you're having trouble finding group members, either to add to your group or just to join a group, if under the group module, the final project module, there's a spreadsheet that I've linked there. It's also in, I think, the latest Canvas announcement, where it's kind of a clearinghouse where you can put your name down to say, I'm looking for a group, or I'm looking to add a group member to my existing group, and hopefully put people in contact with each other. Of course, you can feel free to use discussions, Slack, etc. For the deliverables here, so in about 1.5 weeks or so, everybody will have to submit the names of who's going to be in their group. So that's everyone submits that, not just one person in the group. And that way it can make sure everybody agrees on who's in their group. Once I get that, I'll be able to create a group in groups in Canvas, so that most of the rest of these things will be group projects where only one person will have to upload. So that's the nearest thing. about, I don't know, a week and a half or so after that, maybe a little longer than that, this input modeling report is due. And this basically is a very short document, and you can find information about it online, a couple of pages, maybe like 2, that gives me a description of the system you want to model, sort of motivates why you're modeling that system, and then lists, these are my input variables that I'm going to need to model in simulation. These are my output variables that I'm going to need to take data on, but I'll use to compare to my simulation to validate the simulation. And here I've gone out and I've actually taken some data on a couple of my input variables, not necessarily all of them, but a couple of them, and shown you that I have the ability to fit models to them. So this input modeling report helps me assess the feasibility of the problem that you've picked. And so I will read through these and I'll say, yeah, that seems like a totally tractable system for this short half-term project. And then seeing how you fit the models, and I can see, and it looks like you already have got some momentum going where you'll be able to gather these data and then start putting it into Arena. So that's really kind of the goal here. And then otherwise, I kind of leave you alone after that. And so the only other deliverables that you have are the end of the semester. So in the middle of the last week of class, there's oral presentations and final reports. They're due Wednesday of the last week of class. And I say oral presentations, but you'll be uploading a presentation to Canvas. You're not going to be presenting in front of everyone. And then what we do then is I assign randomly peer reviews where every individual will have to peer review a report and a presentation from another group. And you'll do that peer review through the Canvas peer review system. I'll collect all those peer reviews. And then after I review all the reports and presentations, in my assessment of the score, I'll also factor in some of the peer review scores into that as well. So you'll get credit for doing the peer review, and part of your score will be an aggregate of the peer reviews that looked at yours. And so if everybody's got about 4 people in their group, we randomly assign all these things, and you'll end up getting about 4 peer reviews per group. It's in per report and per report and per presentation. So that's how we do that. We don't burn any class time to do the presentations, and you don't have to worry about standing up in front of a bunch of people or sitting and having to watch a gazillion presentations all in one day. And that allows us the time to structure the final exam as a stage 2 exam, so we can use that lecture period that would be used for presentations for the multi-stage exam. So that's why it's designed this way. So yeah, minor other details here. The oral presentations will just be 10 minutes. Do not go over 10 minutes. Nobody ever complained that the presentation was too short. But if you do, go well under 10 minutes, you don't compare. Nobody complains at the time of a presentation being too short, but details being left out. So your presentation needs to be complete, but it shouldn't go over this 10 minutes, because that's all that I'm going to hold you accountable for reviewing. So you can just review up to 10 minutes and hit stop. So of course, it's not going to be a hard thing where you're going to have points deducted, but if your peer reviewer watches up to 10 minutes and a bunch of questions are left, unanswered, they can stop there and fill out the rubric and say, you know what, I really had no idea what the results were because they're at minute 14 or something, and I didn't watch that far, and that's totally reasonable. So the written group report also has a limit of 4 pages. And so you can add things to the appendix, and there's more details online about this. And it's very specific format. So look online, like it's got certain sections that need to be in there in a certain order. And you can't go over again this 4 pages. And so that's supposed to keep the reading load down on the peer review and also keep the writing load down. And I think it ends up making for better reports when we constrain the length. All right, and I think, get the names of your team members ASAP. You may have to learn a little bit more Arena on your own, because we may not cover everything you need for your particular system, but when those things come up and you're like, I don't really know how to do this thing, let me know or let the TA know, and we can help you say, all right, well, you should look into this thing that we haven't talked about in lab, but is an easy to use tool that's in Arena. So we can help you through that so you can learn a little bit more. All right, so any questions about the final project stuff? I was going to step back and see if there's questions online. Questions in class? Okay. All right, so otherwise assignments moving forward, standard ICA schedule. There's a couple ICAs that are available for you. So there's this ICA G3, which will be due in a couple of lectures, H, J1, J3, L, and that's it. L, I think, is the, well, I think M is the final project or the final review ICA, similar to the midterm one. So that'll become available after L closes. But that's all of the ICAs left. The next homework, homework G3, I haven't made available yet. I'm still working on editing it. I should have it available by next week. It's technically not released until a week from today anyway. And you'll get 2 weeks to do G3. There'll be some things like doing a chi-square test on a non-uniform distribution, things that you've already done before in like 380. And some other things like doing a power analysis, which I'm pretty sure you probably haven't done before. But so that will be kind of the second part of this one, a power analysis. And then after that, there's homework J2, and that's the final homework. No more homeworks for the rest of the semester. So if you missed a homework or anything like that, then definitely make sure that you complete these last 2 homeworks, because that's it. And then again, keep thinking about your final projects. So that's kind of moving forward. So that's the schedule moving forward. Any questions? Okay. All right. So where we left off last time, right before the midterm, we had covered random variate generation. So hopefully this picture makes sense to you. This idea that if the computer gives us uniformly distributed random numbers between 0 and 1, we can invert a CDF to get whatever distribution that we want out. Basic idea here, if I were to give you a PDF like this one, a probability density function like this one, if you need to generate the CDF, you're taking the integral underneath this funny thing, and this is just a trapezoid. So if I'm taking the integral from negative infinity up to a point on this sort of triangular piece, then the area is just going to be that fraction of the triangle. So if you think about it, the base is x, the height is x, and so the area of the triangle is 1/2 x squared. I don't even have to do an integral to do that. So just geometrically, I can see that from 0 to 1, then the CDF is just the area of that triangle. And then so for that region, just up from 0 to 1, I can invert that to generate my inverse CDF. So I just set R equal to that thing, and that's what just goes on here. Because the x's are all positive, I'm going to select the plus so that I have x is equal to square root of 2r. And that tells me that for x from 0 to 1, r is going to go from 0 to 0.5. And so that part of the task is done. So then I say, well, what do I do for the upper half here? Well, now the area underneath that curve is just all of the triangle plus this little rectangular fraction. So what's all of the triangle? The area of that triangle is just the base. One leg is 1, the other leg is 1. So the area of that triangle is 1/2. That's what the blue is there, 1/2. Plus this rectangle. That rectangle, one side is x minus 1, the other side is 1. So there it is, the area of the rectangle. So that right there is your CDF for this portion from 1 to 1.5. Again, you don't have to do any calculus, just use geometry to figure out that CDF. And then so I can then invert that, setting that equal to r. And when I do that, and I get some expression, x is equal to r plus 1/2, and that confirms that for this range from 1 to 1.5, we fill out the rest of the r from 0.5 to 1. So now we've got this expression of our inverse CDF that we can now use to generate samples from this PDF. And we've learned how to do that, in Excel, generate random numbers in a column, generate another column that encodes this inverse CDF in an if statement, draw a bunch of rows, and we can generate histograms. That used to be to generate a histogram in Excel, you had to do kind of a complex thing here, but now you can just highlight a column and it's one of the chart types, it's histogram. So it's pretty easy to do. And you get something that looks like this. And so as expected, it ramps up to 1 and then it flattens out, just like we were expecting. So, that brings us through kind of where we were there. If I wanted to implement that in, say, MATLAB, here's how I would implement that in MATLAB. Same sort of thing. I generate a bunch of random numbers between 0 and 1, and then I fill in x values so that The R values that are less than 0.5 get one formula, greater than 0.5 get another formula, and then I do a histogram, and I get a histogram similar to that. I can also do it in ARENA. And so ARENA does not have this inverse CDF preloaded into it. So if I have modeled a system that needs this probability, the probability density function that corresponds to this, so in other words, this random variable, I am going to need to manually implement this the same way that I just did in MATLAB or Excel. And one way I can do that in ARENA is using an assign block. I can assign RA is shorthand in ARENA for a uniformly distributed random number. So in this assign block, it runs down through the assignments from top to bottom. It assigns a random number to R. And then I then assign a variable called trap delay to this formula here. And if you look at this formula, it just says, if R is less than 0.05, use this formula. Otherwise, if R is greater than 0.05, use this formula. This is something called disjunctive normal form, when you put the conditions as that you're multiplying the conditions through. So this condition zeroes out when it's not true. This condition zeroes out when it's not true. So when I add the whole things up together, I effectively implement this piecewise function. And if I do that, then I can actually have ARENA do a histogram, and you're going to learn how to do that in Lab 7. And so if I do a histogram of the trap delays that come out of that, as expected, it ramps up and then levels off. So a bunch of different ways that I can do that. And so that was with one example. And so if you need another example, I won't go through all the details here, but I can do the exact same thing with this trapezoid, flip the other way. So if I were to go down through that, if you're looking for more examples of how to do a random variate generation, I've got it here. And so I end up getting something that says, well, all right, so I know how to, if you give me this inverse CDF, I can generate these data points. Great. But the big question is, how do I, one, validate that, that these data points match up to this hypothetical distribution? And then how do I pick this hypothetical distribution to begin with? And so I start with that first problem. How do I compare? Like, imagine this is real world data, and I think this is the right model. How do I compare this model to say, is this really what's going on in these real world data? Or if I view this as the output of VinSim, and I want to make sure, or not VinSim, sorry, it's a different sim package, the output of ARENA, and I just want to make sure that ARENA didn't screw up or there's no bug in my implementation. How do I make sure that this distribution, it definitely matches this distribution? That's one thing that we need to handle in this unit. Now, we've already learned how to do that with this. So this is a uniform distribution between 0 and 1. And these are data that might be uniformly distributed. Well, we already have a tool that allows us to do this. We can take a chi-squared analysis. We can do a chi-squared test on these data with this hypothesis and evaluate whether those match up. Or we can do a KS test. So one of the things we're going to be learning how to do in this unit is how to take the chi-squared and the KS test and apply them to more generic distributions like this one, so that we can ask, do these things match up? So that's one thing we have to do. The other thing we have to do is just figure out how to pick these things to begin with. And so how do we, look at data, and from that data say, that's, this is, that's definitely this over this, and vice versa. Or how do we tell the difference between an exponential and a libel? How do we even get started with picking these hypothetical models? And that's also the thing that we're going to be doing in this unit, Unit G. All right, so that brings us up to where we want to start for the new material. Are there any questions about any of that? Anybody still feel murky about random variate generation or the general idea behind input modeling? Any of this ringing sort of hollow? I was pretty happy with the random variate generation solutions on the midterm, so I feel like hopefully everybody is feeling okay with that. And I think the input modeling questions are pretty decent too. So hopefully we're heading in the right direction. All right. So So let's get started on this input modeling then. So here's a simple problem that I've brought up before. A very simple model of either an airport or a security at, say, a government building. You've got passengers that arrive at, say, an airport. They get checked for ID. Some of them pass security and get cleared. Other ones go through, or other ones are denied and have to go through some other process or just get kicked out of the building. And so we've got three input models that we have to deal with. How frequently do they arrive? How long does it take to check each of their IDs? And how many of them actually pass security? Those are all going to be random variables that we need to model to match reality. So if we focus just on passengers arriving to security, we've talked about this here, where some of the passengers, if we think about their average arrival rate, say it's 5 passengers per hour, you're gonna have some passengers that are gonna have more than that in between them, some passengers will have less than that in between them. And if we histogram all of those inter-arrival times, then we might get something that looks like an exponential. So in this unit, we're gonna start with these histograms and then come up with intelligent ways to pick out what distributions best fit these histograms. And in this case, let's say it's an exponential. Once we've picked that exponential, there are going to be a bunch of different exponentials in that family. So it's kind of like there's a bunch of different individuals in a family, but they're different heights. And so you could say, well, I need the member of the family that is 6 feet tall. Well, that might be Joe. The member of the family that is, 3 foot tall. Well, that might be little Jill or something like that. And so similarly, the family of exponentials is parameterized by their averages. So we'll say that this is not only an exponential, but the exponential that is best like our real data is the exponential with an average of 19.88. So we'll have to figure out how to come up with that parameter. Once we have the family and all of its parameters, we'll be able to go into Arena and like you've already started to do in your labs, and be able to say for passengers arrived to security, we're going to say it's an exponential, it has this parameter, it has these units, have to make sure we're careful about the units, and that allows us to simulate arrivals that hopefully match what goes on in the real world. And so that's kind of our big thing here. So we're coming up with these probabilistic models that we pipe into some logic that represents the flow of individuals through airports and other systems, manufacturing systems, and so on. And then we're going to get simulated data out. And that simulated data out is going to itself be variable. And so as hopefully you saw in lab 6, part 1, I gave you one system, but I had you try it with different distributions that all maybe had the same mean, and they had different outputs. And so this is an example of how just knowing the mean isn't really that useful. This is one of these things where, unfortunately, the physicists got to modeling first. And like so many other things, the physicists ruined it for everybody else. Because physics is so simple. If I take that skateboard and throw it through the air, it'll tip end over, I'm not going to, but it'll tip end over end. But nobody cares about how it's tipping, because if you know the center of gravity of that skateboard, you can follow it and it'll be a nice, beautiful parabola. It'll be something you could draw on a piece of paper, and it would just follow that arc perfectly. So physicists look at the world and they don't see the complexity that we do. They see center of masses. They see a point on that skateboard that if you throw it, you can follow the point and you know everything you need to know. And yeah, you can sort of solve for all this stuff, but physicists are more into like back of the envelope stuff. They really only care about the center of that skateboard as it flies through the air. But the rest of the world, that center of the skateboard, that's the mean of the skateboard. So physicists basically said the whole world, 90% of the world, can be explained by average behavior. And they came to modeling first, and they convinced the rest of the world that that's the way we think about the world, is in terms of averages. And unfortunately, the rest of the world doesn't work that way. And so I'm hoping we can start seeing that, is that knowing the average is usually not enough to best predict what's actually going to happen in a real system. We do care about where the rest of that skateboard's going. Knowing the average value of where a mob of people are doesn't really tell you about the mob of people because they're going to spread out. You know, they're going to act like this nice rigid skateboard. So we really do care about distributions. And so input distributions matter and output distributions matter. Means do not matter. But unfortunately, your stakeholders have been trained by physicists, probably in elementary school or high school, to just ask for the average. And so we have to deal with a community of people who have been taught that the average is all that they care about. And that's why we have to give them averages. But we always have to temper that with half-widths. So we're going to learn through the rest of this semester how to start with point estimates, averages, and then graduate to interval estimates, which really capture our uncertainty and the variability in real-world systems. And so when you look at these outputs, I beg you, don't be a physicist. The world is much more complicated than physics. Don't just pay attention to the average column in ARENA. Pay attention to the variability in your output. The variability in your input will generate different variability in the output. Inputs with the same average but different distributions generate different outputs. So variability matters. Average is not enough. It's not a physics class. All right, and so that kind of, it dovetails into if you pick the wrong inputs, you're going to get the wrong outputs. And that's our GIGO property, garbage in, garbage out. So just like it's a great idea to put clothing on a human to see what the clothing might look like, as opposed to just laid out on a table. But if you choose the wrong human, you're going to get the wrong inference. And so that's the same idea here. So, and this is kind of summarized by this stuff here. You can take bad assumptions and you can dress them up. But no matter how nice the visuals are, it's not going to be a useful model in the end if it started out with bad assumptions. So that's really what this whole unit is about, is getting rid of our bad assumptions, finding out the right ways to choose the right distributions that we could put on the inputs. So that's what we're doing. So input modeling is what this whole unit is about. Hopefully you get now that this is selecting the right probabilistic models that mimic realistic variation. In different types of systems, we have different traditional input models that we have to work with. So if you're modeling a queuing system, there might be a lot of input models, but almost always you're going to have inter-arrival times and service times. So that, if you're thinking about your final project and you say this final project is basically a big queuing network, you got to know that you're going to need to go out and take data on inter-arrival times and service times. If you're modeling a supply chain problem, inventory management problem, you know that you're going to need to model demand variability and lead time variability. If you're modeling something that fails, like machine failures and those sorts of things, you're going to need to probably model how often that machine fails, failure times. And so certain types of problems always have certain types of input models, maybe plus a few more. And so we try to pick a distribution, not just a mean. So maybe that's exponential, maybe that's normal, et cetera, that helps capture this variability without having to go into great detail about what's going on underneath it all that drive this variability truly. So that's our overview. Are there any questions about this general picture of what I mean by input modeling, how to put these things into ARENA, what the ultimate goals are? Okay. So this unit is split up basically so today we're going to talk a little bit about collecting data from the system. The next lecture on Tuesday, we're going to talk about actually picking the right probability distribution from all those families. And then so we'll talk about things like PP plots, QQ plots, and so on. And then once we get through that, finding the right family, then in lecture G3, we'll talk about actually parameterizing. So coming up with the right parameters for that family, and then evaluating our choice rigorously using goodness of fit. So that's where the chi-squared and the KS test will come back to us, and we'll introduce the idea of statistical power. And so that's when we'll start talking about that. So let's talk a little bit about data. Have you think about some things here, and I'm going to ask a few questions. So, some examples here of just because data is available, it's not always relevant. So here's an example that's actually kind of taken out of the book here. A simulation study will investigate how to reduce time patients wait in a clinic. So again, think about your final projects. This would be like a good final project thing. Like, do you have data on a clinic or something clinic-like? I've actually had students that worked with clinics to get data and actually did this modeling problem for their final project, or a more complex version of it. So here we got the entities going to the system are patients, and those patients have to get matched up with a nurse who takes their history. And so that's, we're just focusing on the activity of taking the history. So they might wait in the lobby, that's the delay, that's an output. The input, the activity, is when they actually meet up with the nurse takes their history. Now, we'd like to model this, and so when you go to the stakeholder, you go to the clinic and say, I need to take data on how long it takes for different nurses with different patients to take this history so I can get a distribution of these times. The stakeholder comes back and says, hey, wait, a prior 2002 study, so what, 20 years ago now, already collected these data. So, so we have the data, it's still available. And the question is it good enough? Can we just cut corners and use this data? Why might this data not be good enough for this study? What might be wrong about using 2002 data for a study on taking patient history in a modern clinic now? Yeah. You have sort of examples of how, so for those of you here, I'm saying 20 years ago, things could have been very different. So in like how the clinic is run. So do you maybe have some thoughts about what one thing might be different that could create? Yeah, so that's a great, and so that's one thing we could say, well, in 2002, you walk in and all the patient data is on paper, they fill out forms. But now, you know, they're using maybe tablets to take all the history. Maybe there was a transient period in 2010 where everything was on a computer that was bolted to the wall that they pulled out. And now things are very different. You know, again, they got these sort of tablet things. Maybe a lot of the history that was taken in 2002 was stuff that could be gathered ahead of time as patients fill out forms before they even arrive. So the point here is that the processes can be totally different. If, you know, even though the data, like the system, think about, this is like lab 6, part 1. The system is identical, like the flow, the logic, what you draw in ARENA, the decision tree, those things, those are identical between 2002 and 2022. But what changed is the timing, the input models, how long it takes for an individual nurse to take an individual history. And so that's an example here where we probably cannot use these data. Another example, this is taken from a colleague who did consulting work for a company in Georgia that made carpet tiles. And he had to go in and model the relationship between temperature and adhesion of the carpet tiles. And they gave him a bunch of data because they did not want to pay for him to do a study, to run this study again. And he took the data and he said there's no relationship, weirdly enough, between temperature and the carpet tile adhesion. And when he talked to the engineers on this, they said, oh, no, we know there's a relationship because when we generated the process that generated that data, we tightly controlled temperature so that it didn't vary, or else we would have problems with adhesion. So that was an example where he had a whole huge data set that had no significant variability in temperature. And so because of that, he couldn't detect a relationship between temperature and adhesion. And that's because they took the data on a system that artificially constrained temperature, so there was no variability. So you always have to ask, under what conditions were these data taken? And does that, you know, does it invalidate those data for now? Are there any questions about that? Does that make sense what I mean? Just because data is there and just because it's costly to take new data doesn't mean you should use the old data. Okay. So the other thing, summary statistics. I've already kind of talked about how physicists ruin the world, and this is along those lines. This is simulation study. Will assess how new security protocols being implemented on a metal detector feeding a government building, entities, people, activities, how long it takes for them to pass through the metal detector. Now, again, you would like to run this study, or maybe you did run this study, 1,000 observations, and very quickly you pull out the mean and standard deviation, and you say, oh, the mean and standard deviation of these 1,000 observations are nearly identical. And then you just think, of all of the distributions that I learned, what are continuous distributions that have an identical mean and standard deviation? Well, they're very few, but you know, the exponential is one of them. So you're tempted to use an exponential for that. But then when you look at the mean time, it's 30 seconds. So if you think about that, you know, if you've got an exponential distribution, so let's see if this works here. So if you've got an exponential distribution that looks something like this, where this is time, that's supposed to be time, and you know, and this is the frequency, so this is the PDF, and the average here is 30 seconds. Then if we think about that exponential distribution, then that means there are a bunch of outcomes that are way out here at like 180 seconds. And there's still plenty of outcomes that are like here at like 5 seconds. So you might think 30 seconds seems like a little long for me to walk through a metal detector, but it might be viable. But when you then look at this distribution here, you'd say it's not going to take you 3 minutes to walk through a metal detector. So it kind of makes me question whether an exponential was the right choice for this. So that's the, you know, summary statistics alone can lead you down this sort of bad path, which is why we typically, let's get rid of this here, bring the chat back up. So typically, we want to use a histogram first, just to sort of do a sanity check. And we do a histogram of these things, and it turns out the distribution is bimodal. So it's got 2 humps. So I guess if I were to draw that on here. So by bimodal, I mean, if I put the PDF up here, then I'm going to see that maybe it looks kind of exponential-like, but then there's another hump out here. And so this mean ends up being 30 seconds. But this, you know, but this whole group is really clustered maybe closer to 5 seconds, and this group over here might be clustered at, I don't know, 120 seconds or something. And so when you take those 2 times together, the center of mass is at this weird point in between where it's about 30 seconds. But really, when I look at it, I say, really, you know, there's 2 populations here that I'm observing on top of each other. I'm observing a population of those who go directly through the metal detector in roughly 5 seconds. Metal detector, it doesn't take you that long to walk. And then I'm looking at another group of people who maybe got flagged and are checked for extra, you know, screening before then they're allowed to walk through. So this other hump over here is metal detector plus additional screening. And so that tells me that I need to restructure my simulation logic. It's not, I just don't need to find an input model that matches this thing up. I might need to come up with 2 or 3 input models. An input model for the short times, an input model for the long times, an input model describing how frequently they get flagged. And so what went from 1 input model after I looked at a histogram became 3 input models. So that's why these histograms, like looking at the spread of the data, the distribution of the data is so important. It is one of the first things you should do. Summary statistics are not the full story. So let me clear that. Are there any questions about that? All right, and we will actually do this process in ARENA next lecture. We'll break this apart and look at how we would rebuild an ARENA model after seeing this. All right, and then the other thing is I might look at these 1,000 observations and I see that some of these times are negative. Well, it should never take you negative time to go through a metal detector. And so that tells me that maybe I need to look at how we took the data, and maybe whoever was entering in the data sometimes flipped. You know, if they had a stopwatch and they said, okay, they entered at this time and they exited at this time, then maybe sometimes they flipped which time was which. And if it's a systematic thing like that, maybe I just flip them back and everything's fine. Maybe someone wrote in the wrong number and I have no idea what the right number is. Well, in that case, maybe I should just discard that data completely because I don't want it influencing my models there. But it gets a little more complicated because it might be that some of these discarded data still allow me to infer who is flagged by the metal detector and who is not. So is it okay that I use 60 data points for the passage time model, but 80 data points for estimating the probability of going through the metal detector? Doesn't matter that much. Can I try the model with and without that and see if they change? These are not easy questions, and I don't have a general rule for these things. They often are going to differ in your different application spaces, but you need to be looking out for them. So, so look out for negative data when data shouldn't be negative. Don't just let it go, because Arena will have no problems like generating negative data if you've managed to fit a distribution that sometimes generates it. But then if your stakeholder notices that now you're simulating negative passage times, it totally makes you look like an untrustworthy modeler, because that should never happen. So don't just blindly trust your data. Make sure that your data is good before you build something that mimics that data. That's what I'm kind of saying here. All right, so any questions about that? Those examples? Hopefully pretty straightforward. All right. Okay, so how do we take data? How will you take data as you're collecting data for your final projects? Well, the first thing I'm going to recommend you do when you come together with your team is, before you even do any costly data collection, go out to the system that you have selected and just watch it for a little bit. So, sit there for a half hour, do some planning, see some of the weirdest things that happen, and make sure you've accounted for all of the processes that you think are there. Then as you start collecting data, you have to be careful about this, because you don't want to sort of bias your results. But if you're doing a costly collection, maybe you should start looking at it a little bit as you're collecting it to make sure, are you generating negative numbers? Is this going to be adequate? At this rate, are we not actually going to be able to fit a distribution because we're not going to have to do, how are we going to gather enough data? Is there some other data that we can gather that would be more informative, and so on? So start looking at the data. Don't just trust that it's going to work out. Try to, as you're collecting it, does it pass the sniff test? Check for what is called homogeneity and pool data whenever possible. So I've talked about this before. This is especially good for inter-arrival data. You might find that you've taken some data on a Monday at a restaurant in between 3 and 4 p.m. and you go there at Tuesday between 3 and 4 p.m. Well, if the 3 and 4 p.m. data look very similar on both days, then it may not be worthwhile to have a separate Monday model and a Tuesday model. You can just have a weekday model, and you can take all of that data together, and that will make a better fit. You probably can't do that when it goes into the weekend. So you might need a weekday and a weekend model, but pooling data gives you more data, so you'll have actually lower confidence intervals, and you'll have like tighter confidence intervals and better fits. Similarly, per hour, you should start out assuming every hour is different, from 9 to 10, from 10 to 11, and so on. But if you start noticing that the distributions look very similar, and you can do statistical tests to actually confirm that they're similar, then you could say, well, actually 9 and 10 and 10 to 11 are very similar. I'm going to pool those together and call that morning. 11 to 12, 12 to 1, 1 to 2, those are all actually really similar. We're going to call that lunch or something like that. And if you can group them together, you get more data and for better fits. And it makes your model simpler because you don't need as many input models. So whenever possible, try to bundle data together to make for more data and less input models, but do not assume you can do it ahead of time. Don't immediately assume every hour of the day is going to be the same. I don't want you going out and collecting data at 9 a.m. one day and at 3 p.m. the other day and at 5 p.m. another day, and then just putting them all in the same data sheet and assuming that all of those can be grouped together as one input model. Because very often that won't be the case, especially for inter-arrival times. So are there any questions about this idea of what I mean for check for homogeneity and pool data only when it's homogeneous, when it's homogeneous? Does that make sense, this basic idea? It'll save you a lot of work, but if you do it prematurely, it'll probably cost you some points. All right, and then be aware of data censoring. So this is a big problem with failure time distribution. So this is a big problem for inter-arrivals. This is a problem with failure time distribution. And so what I mean by that is if you're modeling a failure process, you can't sit there forever. And so you might assume that, if you observed that whenever you turned a device on, you're seeing how long it takes for it to fail, there are going to be certain devices that never fail during the observation period. And so you might assume that, effectively that they never failed, when in reality, they might have failed a minute after you stopped observing them. And so if you only include those that failed and not those that didn't fail, you can bias your failure time distribution to being way too short. And so it's a little bit beyond the scope of this class, but there are things called like failure analysis. There are Cox proportional hazard methods. There are statistical methods that can actually deal directly with this censoring problem. And just for now, I want you to be aware that the censoring problem is there. And if it seems to be a problem for your model, you can come and talk to me and we can figure out a good way to compensate for that for your particular simulation model. But I just want you to at least be aware of the problem, even though we're not going to necessarily talk about the exact solution for it in this class, but we can on a one-on-one. And then the other thing is look for relationships between variables. And so this is something that is really important. If you take two variables, data on two variables that are out there, it's often, you often assume that they're independent. So for example, if I have inter-arrival time and service time, I might assume that if I take every individual's inter-arrival time, like how long we had to wait for them to arrive after the previous individual, and then I pair them up with their service time, so how long did that person's order take to make, then I might assume that there's no relationship. And that's what this cloud looks like here. So this cloud is dense in the middle where the means overlap here, but there's no structure to it. And so if a high arrival time is just as likely to correspond to a low service time or a high service time. So that's what I mean, that there's no relationship between inter-arrival time and service time. But if you actually plot these things out, what you might see is something that looks more cigar-shaped, like this. And what that indicates is that there is a relationship that needs to be modeled in your ARENA model. So if you notice that long inter-arrival times usually correspond to orders that happen to also take a long time to make, I mean, that's kind of a weird thing, like why would that happen? But if you notice that, then we have to think we may need to model that in ARENA. Similarly here, if short inter-arrival times pretty much only correspond to short service times. So that's definitely a pattern you need to look for, is that you've got data that you've collected on like one individual, multiple data points. That's really a key to say, do these data points correlate, so that for every individual, if you know one, can you predict the other? So before I move on to show how we might deal with that in ARENA, do these plots make sense to everybody? These are plots that I might throw up on a final exam. I might say like, here's a bunch of scatter plots where these sort of multi histogram plots here. Which one of these represents data that are independent or that are dependent or have a negative dependence and things like that? So do these plots make sense? Are there questions about these things? So hopefully you can see here that like this is the marginal histogram of inter-arrival time. This is a marginal histogram of service time. This histogram is identical to this one. This histogram is identical to this one. The only thing that differs between these two data is there is a correlation between these data and these. And then here I've basically randomized these things so that there's no correlation between these and these. But it's the same set of data points for inter-arrival time and the same set of data points for service time. There's just relationship here, but none here. Okay, no questions. All right. So how might we deal with that? Well, I skipped over this in lecture E2 because it was a little bit beyond the scope of the class, but there is something called NORTA, which is a stochastic simulation method that can implement correlations. If you take a more advanced sim course, you'll probably do some exercises using NORTA, but it's a little complex in coming up with these correlations. So especially for our class, it's a little better to build a kind of a simpler statistical relationship where I might say, you know what, I'm going to model service time as being a linearly related to inter-arrival time with a little bit of noise. So here, rather than modeling service time as a totally independent variable, I can effectively not build an input model for service time and instead say whatever my inter-arrival time is, multiply it by 2.5 and add a little bit of noise where the noise has got a mean of 2 and a variance of 1. So that means that now my input modeling problem is coming up with this relationship, this 2.5, which is like the slope of this cigar, and the magnitude of this variance being added, which is kind of the fatness of this cigar. And if I do that, then every inter-arrival time that comes in, that's sort of the independent thing. And then service time gets chained to the inter-arrival time, where the slack is the normal, but then otherwise the relationship's captured by that relationship. So we can actually implement this in ARENA as an expression instead of drawing a fresh random variable. All right, so there are questions about that. Does that make sense about I can implement service time as being a function of another random variable in ARENA as opposed to drawing it fresh as a new random variable? And I think I've got an example of that here. So like in ARENA, I can create an attribute that rides along with every entity, and that entity's attribute will capture its inter-arrival time. And then as that entity goes through a process that it needs to know its service time, instead of drawing it from a service time, I use expression, and then I put this expression in 2.5 times the attribute inter-arrival time plus norm 2.1, and that will implement this relationship, and then that will end up giving me a service time which is related to the inter-arrival time but doesn't draw it totally independently from its own distribution. And then for validation, I can compare our simulated service time with that marginal distribution of service time that I got from the real data. So any questions about that? Does that basic structure make sense? Okay. The other correlations we need to worry about are correlations in time. So when you're taking your data, don't just plot them against each other, plot them over time. And so I might have something here, which might be service times, for example, and this here might be sample numbers. This might be the customer IDs. So I might expect that every customer is going to order something different. So their service times are going to be all over the place. And that's sort of what I would get here. This is what it would look like for independent samples. And so the 100th customer, their service time was up here, 101 was down here, 102 might have been over here, but I can't predict the next service time from the previous one's service time. Now, in reality, a lot of times a customer hears the order of the person in front of them and says, you know what, maybe I'll change my order to that. And you can get correlations over time. So this is without those correlations, as if the customer is totally unrelated to the customer in front of them. But even without that, there could be temporal relationships. Like at lunchtime, people are more often order sandwiches. After lunch, they're more often order coffees. So there can be a temporal relationship where if you know that somebody's ordering a coffee, it's a pretty good idea that the next order will also be a coffee. So if you get this is what we call white noise. And so, independence over time is called white. And that's because if you look at its spectrum, if you use linear algebra and you decompose it into spectral components, you'll have a spectrum everywhere. So it's kind of like your cell phone. You've got a 5G cell phone. Maybe in the corner it says 5G UW, ultra wide. That means that your cell phone uses a huge amount of spectrum, and and once you start using a flat amount of spectrum, we start calling it white. So this is what we mean by white noise. It means things are independent over time. So if I were to take a sample value at any time and look at the histogram of like the sample values, say around 200, and I were to plot them again, the sample times around 300, then regardless of what distance I put in between them, I would always get no relationship. Now, it might be that there is a relationship. So like I said, breakfast orders are very similar, lunch orders are very similar, and so on. So service times tend to stick around each other. They drift up a little bit with very little bits of diffusion, but there are these sort of drift components that make it almost look sinusoidal. And if I now were to plot the service time at one time, a distribution around 200, versus the service time at another time, say 10 samples later, then now I actually find that a service time at one time is very related to the service time 10 samples later. I get a cigar-shaped thing here. And if I were to plot what's called a correllogram, which plots that relationship over time, then I get something that looks like this, where what I'm looking at here is the number of samples in between is plotted here on the x-axis, and the amount of correlations plotted on the y-axis. And so a sample is 100% correlated with itself, but a sample 1 or 2 samples later is very tightly correlated, maybe 80% or 60% correlated with that same. You don't actually go down to 0% correlation until you get down to, I don't know, 50 samples away or so. And even after that, there's still peaks over here. And so really you don't start totally dropping off on correlation until like 1,000 customers later. So this means that, every 1,000 customers, there actually have orders that are related to each other. And so we need to simulate that, because if we put this into our simulation model, we'll get very different results than when we put this in our simulation model. So the way we implement that is we have to come up with a model over time. And so what we can do is something like this in ARENA. We can say, well, ARENA's got a variable called T now, which is sort of the time since the beginning of the simulation. And so I can sort of say, well, if I know the time, in a 24-hour period, let's say I want things to simulate, so every morning I get very similar service times, then I can take my T now, which might be in terms of hours, divide it by 24, and that'll tell me where I am in my day. And then I can put that inside a cosine. And so T now divided by 24, when put inside a cosine, is going to cause a cosine to oscillate where it'll have a period of about a day. And so that allows me to have a forcing function which goes up and down once, one period throughout a whole day. And then I can add a little bit of noise on top of that. And that's one way that I can generate this. There are more sophisticated ways of doing that. So if you take more sophisticated time series analysis courses, you'll learn about ARIMA, autoregressive models, which once you learn how to fit an ARIMA model in one of those courses, you can easily implement it inside ARENA. You can get expressions like this one here, where you can have the price at the next day is 90% of the price at the previous day, plus a little bit of noise. So that's an example of using the previous value to predict the next value. That's what I mean by autoregressive. So these are all patterns that you can implement inside ARENA. This might be the simplest thing to do here, but if you have some insight as to why one customer would be coupled to the previous customer, then you can use this even already. So any questions about this that I mean by correlation over time or autocorrelation? Okay. All right, so last thing, I think, about the last thing I want to sort of cover here before I let you go is, and this is huge, understand the difference between input and output models. We've already seen this a little bit from before the midterm, but I'm just going to keep drilling it down. The input data are your activities. They are the uncertain quantities beyond your control that you can come up with models of before you run your simulation. So you take data on inter-arrival times, service times, fine-grained service times, and you fit models to those. And those models then get implemented in Arena. And then you use Arena to generate the network of all of those things interacting together. You are going to take output data on the real world systems, things like waiting times, queue length, throughput. These are all things you will take on the real world system, but you are not going to fit a model to these. You're going to run your simulation model and compare its waiting times to the real waiting times. And that's how we validate the simulation model. So after we validate the simulation model, then you can use the simulation's waiting times, queue lengths, et cetera, to measure hypothetical performance after you make changes in that sim. But something that's going to happen, and it happens at, every semester, is that when people write their input modeling report, they're going to take data on real world waiting times, queuing lengths, throughput, and they are going to try to fit models. Do not try to fit a model to waiting times, to queue lengths, to whatever. You won't use the model for anything. It's of no value to say there's an exponentially distributed waiting time. Well, those waiting times come out. Well, where are you going to put that exponential in Arena? You're not. You're going to run Arena, and then you're going to take Arena's data and then look at Arena's distribution. So do not fit input models to output data. And definitely, so some people are going to do it at the input modeling report. Hopefully nobody does it in the final project report. So I just want to drill that down. Do not fit input models to output data. Know the difference between inputs and outputs. Super important. All right, so that's basically, my data tips. Next lecture, we're going to start looking at how to histogram, how to use our physical intuition to pick a family, how to then use PP plots and QQ plots to sort of evaluate qualitatively if we pick the right family. So then when we go into Thursday's lecture, how do we then estimate the parameters and then see how well we did? All right, so with that, I'll give you the attendance question, and then I'll be happy to stick around for any questions. Otherwise, I'll let you go for the weekend. So put in the chat the link. And the question I have here is, should you ever fit a model to output data? So should you ever fit a model to output data? That's my question. Yes or no? So an output data is like queue waiting time. Should you ever fit a model to queue waiting time or queue length? Is there any value to that? Should you ever? And hopefully you'll go back a couple of slides and you'll see it big and bold. That's all I've got for you. So if you have any questions, please feel free to come up. Otherwise, I hope you have a nice weekend, and let me know if you have any questions about the midterm or anything else over email, Slack, whatever. Any questions online? And I'll just clarify, output data equals queuing, waiting times. All right, so are there any other questions online? If not, I'm probably going to go and close the room. All right, have a good weekend all.